Look at a standard microcontroller. It processes complex logic routines using a delicate 3.3 volts. Now look at an industrial robotic arm. There is a massive physical gap between these two components. The logic chip processes information using mere milliwatts of power, but moving physical mass requires hundreds or even thousands of watts. You cannot connect them directly. If you pull the current required to spin a motor directly from a microchip, the logic circuitry will vaporize instantly. To solve this, we use an intermediate layer known as power electronics. This is the muscle of the system. It consists of components like driver ICs, MOSFETs, and IGBTs. These devices take low-power digital signals and use them to gate immense flows of raw electrical current. Mastering motor control requires mastering this architecture of energy flow. We can trace this architecture from the ground up, starting with a single direct current switch and scaling all the way to three-phase industrial frequency drives, because power electronics are the only way to translate a digital command into physical execution. The simplest way to control a direct current, or DC motor, is by placing a single transistor in series with it, acting as an electronic switch. But this setup has a critical limitation. Current can only flow in one direction, meaning the motor can only rotate in one direction. To achieve bidirectional control, we need a specific circuit topology known as an H-bridge. This H-bridge diagram shows 4 switches surrounding a motor. In the forward state, closing diagonal switches S1 and S4 routes current left to right, turning it clockwise. To reverse direction, closing S3 and S2 flows current right to left. We can also trigger a break state by closing the bottom 2 switches. This shorts the motor terminals together, rapidly halting any movement. Conversely, opening all 4 switches leaves the motor in a free-running state, allowing it to coast to a stop. The H-bridge routes the direction of the current, but to dictate the motor's actual speed, we need a way to modulate the voltage. We achieve speed control using pulse width modulation, or PWM, which rapidly toggles the power on and off at high frequencies. This raises a question. If the motor is being hit by harsh, discrete blocks of maximum voltage, why doesn't its rotation stutter? This chart illustrates the relationship between raw digital voltage and actual motor current. The blue square waves represent sharp voltage pulses from the logic controller, but the orange line representing motor current doesn't pulse. It rises smoothly and remains continuous. This happens because the motor's coils are inductors. According to the laws of electromagnetism, inductors inherently resist rapid changes in current flow. As a result, the motor physically integrates those high-speed pulses into a steady average torque. Increasing the width of those pulses, the duty cycle, raises the average effective voltage, making the motor spin faster. The motor acts as a natural low-pass filter, translating rigid logic pulses into smooth physical motion. So far, we've treated transistors as perfect switches. In reality, they possess internal resistance and require a physical amount of time to transition between states. Every time a switch operates, power is lost as heat. Total loss comes from 2 factors: conduction loss, which happens while fully closed due to internal resistance, and switching loss, which occurs during the transition and increases linearly with PWM frequency. This creates an engineering trade-off. A higher PWM frequency yields smoother motor control, but it generates significantly more heat, requiring larger heat sinks. Component selection matters here. For low to medium voltages, we rely on MOSFETs because of their high efficiency. But for high-voltage industrial loads, IGBTs provide the necessary robustness. When designing these circuits, we also have to program in dead time, a mandatory microscopic delay inserted between turning off the top transistor and turning on the bottom one in an H-bridge. If that delay isn't there and both vertical switches close simultaneously for even a microsecond, the current will bypass the motor entirely and short-circuit to ground. This is called shoot-through, and it will destroy the circuit. To fine-tune how fast these transitions happen and suppress electrical ringing, engineers place specific gate resistors in front of the transistors. A functional driver requires an integrated solution for thermal dissipation and timing, shifting the challenge from pure programming to physical engineering. Once we lock down these physical rules, we can scale the architecture from basic DC motors to highly precise sequencing systems. This diagram compares 2 types of stepper motors. Notice the bipolar configuration on the right. Because bipolar steppers lack a center tap, they require dual H-bridges. This allows the controller to reverse current through separate magnetic coils in exact sequences, resulting in step-by-step positioning. We applied these exact same principles at the heavy industrial scale using three-phase AC variable frequency drives, or VFDs. This block diagram traces the energy flow of a VFD. Power moves from the rectifier through the DC link and into the inverter. The rectifier's job is simply to take incoming alternating current from the power grid and convert it into direct current. This schematic breaks down the inverter stage. Here, a central microcontroller commands three separate half-bridge gate drivers, labeled U, V, and W. Each driver controls a pair of high-power switches. Together, these 6 switches synthesize a three-phase AC output from the direct current supply. This timing chart illustrates how it works. By offsetting the switching patterns by 60 degrees, the differences in voltage across the terminals create a simulated sine wave. By dynamically varying the frequency of that synthesized wave, the drive gains total control over the speed and torque of massive industrial AC motors. Whether spinning the tiny wheels of a mobile robot or driving heavy factory conveyors, the underlying mechanism is identical, strategically switching and routing power. To guarantee a motor is actually executing its given command, the system must be closed loop, relying on sensors like encoders or current shunts. This flowchart models a closed-loop system, illustrating the constant feedback cycle between physical acting and raw data sensing. The microcontroller continually reads this sensory feedback and instantly adjusts the PWM duty cycle to correct any deviation in speed or position. But this dynamic operation comes with electrical hazards. Every time a switch opens, the motor's inductance generates a voltage spike. We must install flyback diodes to catch these spikes, otherwise they will reflect back and destroy the logic chip. We also implement secondary safeguards, including inline fuses and thermal shutdown circuits, ensuring the system survives unexpected mechanical jams or overheating. Power electronics function as dynamic interfaces, perpetually balancing the constraints of thermal physics against the speed of digital logic. Motor control is the engineering art of directing immense physical energy using